Hello everyone, I'm Zixi Hu from the Mass for Experimental Data Analysis Group. Today I'm going to talk briefly about how advanced correlation analysis reveals the rotational dynamics from X-ray photon correlation spectroscopy data. So first, X-ray photon correlation spectroscopy, abbreviated XPCS, is a super powerful tool for studying particle system dynamics. So in the experiments, we cast a beam of X-ray onto the sample we want to study. This sample usually contains some particle movement that we want to study. And then we can collect the images, a series of images that forms a movie. You can imagine this as taking X-ray images in the hospital, that if you move behind the X-ray images, X-ray camera, well, maybe it's scary, but people will see your skeleton moving on the screen. Of course, this is not recommended by most of the hospital, but in the same spirit, if the particle move in the sample, we will also see tiny fluctuation of the collected images. But something different here is we're not seeing the shade of the molecules directly. We're actually seeing the intensity of the scattered field. So that adds one extra layer of complexity on top of that. So the result is that the collected images fluctuation is very subtle. So from this example, we can see that it shows this noisy, like grainy texture, and it's really hard to pick up any useful information or clear pattern from the collected images by our eyeballs. So in order to analyze these images, we need to calculate the correlation data between the images. And then by analyzing this correlation data, we can reveal information embedded in the collected images, which in turn tells us valuable insight into the sample dynamics that we want to study. So this is a super powerful tool that, like with this technique, we can actually study sample dynamics in nanometer length scale and nanosecond length time scale. So quite powerful. And one fundamental process we can use XPCS to study is the diffusion process, which consists of two components. One is the translational diffusion, and another one is the rotational diffusion. So imagine if we put tiny things in the water, then resulting from the random collision from the water molecules on that tiny things, we would actually see it change its location from time to time, almost randomly. So we call this phenomenon translational diffusion, and it involves the random repositioning. And the rate of this translational diffusion is characterized by the translational diffusion coefficient G. But at the same time, if the particle is non-spherical, we also see its change in its orientation from time to time. So we call this random reorientation rotational diffusion, and it is characterized by the rotational diffusion coefficient dr. So these two processes, the diffusion process, is very fundamental in many research fields. It attracts attention of a lot of researchers. For example, in the molecular biology, it actually affects how the protein or enzyme perform their function in our body. And in material science, knowledge about the diffusion process of these particles can tell us valuable information about the materials' properties, so that we can design more advanced nanomaterials. And it also matters in the chemical engineering, as if we want some chemical reaction to happen, then we need the reaction site on one molecule to bind with another reaction site. So the rate of this binding is affected by how fast this particle can move to the other side and rotate that reaction site to bind with another one. And also, it is quite important in atmospheric science, as it plays a really important role in how the pollution spread into the water or into the air. So that is quite fundamental dynamics we want to study. So how exactly do we study it using the XPCS? Conventionally, we calculate the autocorrelation of these images, which means we pick a specific pixel on the images, and then we calculate the autocorrelation of these images. Well, this will allow us to estimate the translation diffusion coefficient dt very easily. But however, unfortunately, it is not sufficient for revealing any rotational dynamics, because we're not correlating different rotations. We will not be able to see any correlation caused by the rotation of the particles. So to address this gap, we proposed using the angular temporal cross correlation, which generates a four-way data tensor, because actually in order to perform this cross correlation for two different images, we need to pick two different pixels, and then we call it data we collected from these two pixels. So which means, this ends up getting us a four-way data tensor. As a comparison, we can only get a data matrix from the conventional autocorrelation, which means angular temporal cross correlation can give us orders of magnitude more information than the conventional autocorrelation. And luckily, it can help us expose the rotational dynamics. So yeah, it can provide us more information than conventional autocorrelation that cannot access. But the next question is how exactly the rotational diffusion related to the angular temporal cross correlation. So in order to answer this question, we build the following mathematical model to relate the cross correlation and the rotational diffusion. So first, let's assume a diluted monodisperse sample, which means the sample of interest have largely the same shape in the solution media or in the gas. And then we prove there's a limit of infinite number of images, which means in a really ideal case, then we'll have this equation. The left side will be the angular temporal cross correlation introduced in the previous page, and the right side is a complicated series expansion. So the first term in this expression is the social Lagrange polynomial, which is known, and the component and the rotational diffusion coefficient is sitting at the end of these in these decay rate resulted by the rotational diffusion. But before we can actually extract this rotational diffusion coefficient, there's another complicated situation here because the ILM terms in the middle are the spherical harmonic coefficients related to the particle structures. And usually we want to assume that we don't know particle structures, though there are a lot of fascinating, powerful technique can help us extract the structure. But sometimes this is not always available. And if we have a way to avoid this extra cost, then why not? So we assume that we don't know the exact particle structure here, which means we have no prior information about the spherical harmonics, and yet we want to extract this rotation diffusion coefficient from this complicated equation. To do so, to estimate DR, we designed an algorithm called multi-tiered estimation for correlation spectroscopy in 3D. So our MTAC 3D algorithm extracts the desired coefficient from the data tensor in this way. So instead of solving the complicated overall optimization, it decomposes the whole thing into several subparts. And each of the subparts represents a specific constraint we developed from the mathematical model. And each of the subparts can be efficiently toppled with carefully designed projector. Each one of the projector enforces one specific constraint. And then by applying these projectors in a row, the correlation noise projector, the band limiting projector, and the tensor factorization, then we can come to a solution. But we actually want the solution to comply with all the constraints at the same time. So we put these projectors in the loop, which means at the end, we can use the filtered Fourier Bessel coefficient and our current estimate of rotational diffusion coefficient to reconstruct the input data. So by doing so, by performing these projectors in the loop, we can iteratively estimate the rotation diffusion coefficient and also clean our input data. As this is very important that I will show in the next page. So this is the philosophy of MTAC 3D algorithm. To test the capability of this numerical algorithm, we performed a wide range of numerical experiments. To perform this numerical experiments, I majorly simulated two kinds of structures. One is the particle at the left side, consists of 3 crossing nanorods, representing the typical samples we would get from the material science. And at the right side, there's a protein structure I pulled from protein data bank with labeled 1IGT that represents the biological samples. And then here I also show 2 examples of the clean images we get. But however, in practice, we rarely get images like this clean. Usually, we have a lot of different source of noise, background buffer noise or incoherence of light source. And in some really rare case, the detector might be able to pick up something from the cosmic ray. Very rare, but in a real unlikely case, that might happen. So to simulate this situation, I simulate the photon counting noise on top of the clean images to get these noisy images at the right side. So in the example I showed at the left, the sparsity of the images is rendered to about 4%, and the SNR rate is below 1. And the noisy, and at the right side in that image, the sparsity is about only 2%. But yet our algorithm can successfully extract the rotational diffusion. So at the last step, I show a comparison between the input data and the filter data output by our algorithm, and also the ground truth. So we can see even though the input data is very noisy, the filter data overlaps with the truth very well. Shows that our algorithm is really robust to the input data, to the noise in the input data. And thanks to this robustness, our algorithm can estimate the rotational diffusion coefficients very precisely. At the right side, there's a comparison between the ground truth and the estimated values. We can see the estimated values overlap largely with the ground truth, and all the relative values is at most 3%. So after this work, there are a lot of more exciting works ahead. The first is I want to apply this MTAC 3D algorithm to experimental data. For example, the data we collected from advanced light source in our lab, or advanced photon source in argon, or from the free electron laser at LCLS or EuroXFIL. Another direction is to extend the philosophy of this algorithm developed here to the other experimental techniques like cryo-EM, surface scattering, or in ultrasolar. So if you're interested in the method we developed or interested in the background knowledge, or if you have any thoughts, please feel free to contact me and check our GitHub repo. Thank you. Thanks for the attention.